Hello students, welcome back to lecture series on numerical methods. So in our today's video guys, we are going to learn numerical solution for ordinary differential equation. That means what numerical methods are applicable for finding the solution for our ordinary differential equation. Okay, there are several other methods guys, but in our today's video I'm gonna explain to you all one of the finite difference method. Okay, one of the finite difference method. Finite difference method. In my today's video guys, I'm gonna explain to you all one of the finite difference method, which is the Euler method. Okay, which one is the EULER? Okay, Euler method, or we call it as the Euler's method. Okay, Euler's method. This one we are going to learn in detail here guys. Okay, so without further ado, let's get dive into our today's lecture. First of all, we're gonna see the method, and we go for after that some of the example. Okay, yes. So what is this method guys? If we have some sort of differential equation, okay, now consider like the differential equation. We all are familiar with the differential equation. Okay, so let's consider differential equation. Let's consider differential equation. Dy by dx, which is equal to f of xy. Okay, I consider this one as a differential equation. Okay, so differential equation means the differentiation need to be there in our given equation. Okay, so dy by dx, which is equal to f of xy. And if it is a differential equation, that means there is obviously we have some initial condition or boundary condition, something like this. Okay, so consider this boundary condition y of x naught, which is equal to y naught. Okay, y of x naught is equal to y naught. That means the y varies in our different values like x naught, and there are many more values. Okay, so we land on the value of y naught. Okay, yes, so that means these are the different values of x. Okay, x naught, x1, x2, x3. So you will get the different y naught, y1, y2, y3. Okay, so this is the initial condition for this differential equation. Okay, so how one can find the solution for differential equation without actually using the differentiation. Okay, yes, so what do? What we are going to suppose the different value for x. Okay, like x can be x1, x naught plus h, x2, or x naught plus 2h. Okay, so I'm going to consider the different value of x, different value for this x, so we can see what the value for y it is coming. Okay, so if I consider x which is equal to x1, okay, x which is equal to x1, that means x naught is there, you can consider x1. Okay, x1, and we call this one as x naught plus h. Okay, that means if you add something to the x naught, you will get the x naught plus h. Now see that x naught, this one is x naught. Okay, add something here plus h, you will get the x1. Okay, first we consider x naught, and after that you add some h as a constant, you will get the x1. Okay, after that add another constant x naught plus h plus h. Okay, call it as x2. Okay, x naught plus 2h, h plus h means you can call it as the 2h. Okay, x naught plus 2h, which is equal to x2. Again add x naught plus h plus h plus h, which is equal to x3. That means x naught plus 3h, which is equal to x3. So similar like that you have to add the variables. Okay, yes, so you will get the x1, x2, x3. Okay, so in up to the nth term, okay, up to the nth term, you can call it as x naught plus n times h, which is equal to xn. Okay, you can call it as x naught plus n times h as a xn. Okay, these are the variable guys we are going to consider here for this x naught. Okay, yes, so y of x naught is equal to, we get that some different value for y naught. So what are the possible values that we can substitute in our differential equation? Okay, that I have written over here, this one, this one, this one, this one, and this one. Okay, generally these are the value for x. Okay, yes, so let's get start the iteration. So I'm going to explain how the iterations are coming for this differential equation. Okay, dy by dx, which is equal to f of xy. Yes, so what we have, dy by dx, which is equal to f of xy. This one is our differential equation. Okay, so what I want the solution for this one. So in basic things, what we do, if we do not want the dy by dx. Okay, now see that if you want to find out the solution for a given differential equation, you have to eliminate the differentiation. Only then you can get the value for y. Okay, now see that here we have the value for y. That means we have to extract value for y from our given differential equation. Okay, extract value for y. So that we can replace the different value for x for finding the solution of our differential equation. Okay, so you will get the exact solution. Okay, yes. So what we do, we are going to extract value for y from our differential equation. Okay, so in order to extract value of y, okay, that means we have to remove the differentiation, and we know that if we have to remove the differentiation, we apply integration. Okay, but now you can see directly applying integration not possible, like a dy by dx. Okay, it is not possible. So in such a case, we apply variable separation method. Okay, variable separation method. We apply variable separation method. So what we do in a variable separation, we separate dy and dx. Okay, as a numerator and denominator. So I'm going to write dy, which is equal to f of xy dx. Okay, f of xy means this is the function for x and this is the function for y also. Okay, so we want the dx with the function x, so you can take f of xy dx here. Okay, yes. Now see that we have to extract the value for y, so take the integration. Okay, take the integration. Integration. Okay, so integration of dy. Okay, integration of dy, which is equal to integration of f of xy dx. Okay, so now see that as we are finding the integration, okay, over some interval. Okay, over some interval, as we are finding the integration over some interval. Now see that if you are taking integration with respect to dy, you need to have some value for y. Okay, so that you can replace. Now as we are going to find first iteration, that means we start from y0 and we go up to the y1 for dy. Okay, as it is a for first iteration. For first iteration, we start from y0 and we end with the y1. Okay, this is for the dy. Okay, and similarly for dx, this one is for dy. And what is similarly for dx, what do we do? We for first iteration, we start with the x0 and we end with the x1. Okay, as it is our first iteration. Okay, start with the y0, end with y1. Similarly for second iteration, start with the y1, end with y2. And for the dx second iteration, start with the x2, end with the x1 and x2. Okay, start with x1, end with the x2. Okay, so now see that I have the limit for the first iteration, y0 to y1. Okay, and here x0 to x1. So I have these two limits, x0 to x1, y0 to y1. Okay, yes. So apply the limit over that dy. Okay, so integration dy is y. So we have limit y0 to y1, and f of xy dx, we don't have any specific function. That will be the part of your example. Okay, so you can take the value for f of xy from there. So right now we don't have to do anything here. x0 to x1, f of xy dx. Okay, this one is the our next step. Okay, so apply the limit. Okay, y run from y0 to y1 to y0. Okay, so we can write y1 minus y0, which is equal to x0 to x1 f of xy dx. Okay, this one is our first iteration. Okay, now for first iteration, we want the value for y1. Okay, so y1 can be written as y0 plus this minus y0, it goes here to the other side, it gives us the plus y0. Okay, so x0 to x1 f of xy dx. Okay, this one is our first iteration, guys. Okay, and as it is our first iteration now, xy, it is approximate to x0 y0. Okay, as this one is our first iteration, so we instead of xy we can take the x0 y0. Okay, yes, and using this one we can write y1 keep as it is. Y1 we are not going to do anything changes. Okay, y1 which is equal to y0. Okay, plus, so we are taking approximate iteration, okay, so that means y0 plus h into integration x0 to x1 f of xy dx. We are considering it as the x0 y0, okay, so under function x0 y0 f of x0 y0, okay, xy replaced as the f of x0 y0. So this one is our first iteration, okay, h times f of x0 y0. So see that it is easy to remember, not the difficult, okay. Easily you can see y1 is here, y0 here. This integration h into f of x0 y0, h is the step value, okay, here, and f of xy, as it is our first iteration, so we consider xy as the x0 y0, okay. Yes, now let's go for the similar. We have to apply for the similar second interval, okay. There's a value of y at x which is equal to x1 can be calculated, okay, using this one. X which is equal to x1 can be calculated using this one. So we have to go for the similar iteration, okay, for y2, okay. For the second iteration we go for the y2. So y2 can be written as, so see that y1 I replace as a y2, so y0 increase it 1 y1 plus x0 to x1 is there now, so interchange the interval. X0 to x1 can be written as x1 to x2, x1 to x2, x1 to x2 f of xy dx, x1 to x2 f of xy dx. Now see that it is way easier, or you can, if you want, you can take again one more calculation, interchange the interval, you will get the similar step, okay. It's not difficult, guys, okay. So you just have to alternate the interval, okay. So on which interval I'm taking y1 to y2, okay. For y I'm taking y1 to y2, for x I'm taking x1 to x2. Interval changed, guys, okay. Here I take an interval y0 to y1, x0 to x1, okay. So now I'm going to solve for the second interval, so that you can consider y1 to y2, okay, or x1 to x2. This one is our second interval, okay. So this way you can write, okay, and you how to extend this one, okay. So as we have y2, so we write y2 which is equal to y1 plus h f of x1 y1, okay. This one is I written over here, okay. Yes, this one is the value for y2. Similarly you can do it for the value of y3 up to the yn, okay. So yn, it is also easy. So how can I write yn, okay. So now see that if is a y2 is there now, if it is a y2 there, we can write yn plus 1 which is equal to, take 1 reduce from here, so yn plus h of xn yn, okay. This is for n number of iteration, guys, okay. So if you want to find out the 4th, 5th, 6th, 7th iteration, so you just have to replace the value for en, okay. Yes, this one is of Euler method, complete Euler method, guys. I hope you all have understood. It is not that difficult, okay. We proceed after this we proceed in the way we obtain the general formula, okay. This one is the general formula, so en you can replace with the 0, 1, 2 and so on, okay. To obtain the solution with a desired accuracy, we have to take similar values for each, okay. Okay, what we have to do here for this each, to obtain the desired accuracy, we have to take smaller or similar value, similar everywhere but smaller value of each, okay. So hence the solution is obtained very slowly due to this Euler method, okay. So that means the solution, it is coming now after 4th, 5th, 6th, that means it is coming very slowly, okay. The solution for this differential equation gives us the very slowly answer, okay. And it is less accuracy. For if you want more accurate answer, there will be the Euler modify method, okay. For finding more accuracy and plus with a less iteration, we use Euler modified method, okay. Yes, so we take that method in our next lecture, guys. But based on the Euler method, we go for some of the example, okay. Based on the some of the example, okay. We'll see that example in our next lecture, and then after we go for the Euler modified method, okay. So I hope you all have understood my today's lecture, guys, okay. So if you want, you can refer here my entire method. So note it down, guys. These points are very much important. At least you need to know what is the Euler method, okay. It is very much important for your ENDSEM exam. 5 marks question, it is definitely there for this exam method, okay. Yes, I hope you all have understood, guys. Note it down this point, and if you have any doubt, difficulty regarding these points, or if you have any another point that you are coming with doubts, confusion, let me know in my comment section, guys. Okay, I will come up with a similar videos. So that's it for my today's lecture, guys. So thank you everyone. Thank you for my today's lecture.